300 bridges that are affected by floods, and the highways solid waste management, highway and solid waste management in that county. He's a graduate in environmental engineering from Clarkson College, and his topic today, flood recovery, lessons learned along the way. Wayne.
Thank you. And good morning. It's a pleasure to be here today. Some of the things that the first two speakers certainly spoke about, I'm going to drive home. And probably the first and foremost is I graduated from Clarkson College in 1978. And one of the most important things that was said to me at graduation is now you have the right to become an engineer. 35 years later, and I'm still trying. Some of the topics that they requested that I talked about today is how Delaware County has responded to some of our floods, adaptations that we've made to road infrastructure, and I think one of Stuart's points to be taken home from us, or with us as humans, is all these other species have adapted. We have not. And we need to learn. And the question about floodplains and floodplain mapping, and has that, is that changing? As we see climate change and higher flow events happen, that 2 feet of freeboard that we as engineers have given to floodplain is not enough. And we really need to learn as humans to not build in floodplains. I want to introduce some practices that we have outside of culverts and some of the success stories that we have learned. I'll go through a little bit of history, some of the events that we've suffered, certainly our lessons and solutions that we use. Floods are real. This is County Route 16, just outside of the county seat in 2006. We lost over 3/4 of a mile to one of our biggest employers in the county. Right across the hill, Jackson Hill Road over Hudson Valley Creek in the drink. From an engineer owner perspective, these are the things that do 2 things. It's really a challenge as an engineer to try to recover from these things and do it cost effectively and quickly. But from the standpoint of suffering from humans, it really weighs on us. When I graduated, open channel flow was something, hydraulics was something I was very interested in. At the time, trapezoidal channels, the Corps of Engineers was building berms along the Mississippi River. We were designing these trapezoidal channels to carry 100-year events, nice uniform alignments, and we only worried about water. That changed for me in January 19, 1996. With my first opportunity, first flood that I lived through, certainly as a person that was responsible for our infrastructure. We did just what Stuart said. As being a relatively young engineer, I went ahead and tried to put some streams back to help people recover as quickly as possible. And I might have got a little overzealous, and I certainly made a lot of mistakes. So I'm going to tell you what some of those mistakes are today, hopefully prevent you from making them in the future. Since that time, we've suffered 11 federally declared events in 15 years. So if there's anyone that knows how to do it wrong, it's me. We've also had some undeclared events. Some of them very, very intensive events that the Federal Highway Administration declared a few of our roads, but globally throughout the county, we were not covered. June of 2006, Delaware County is a little bigger than the state of Rhode Island. We're about 1,470 square miles. We had $14 million in damage just on the county system alone. 14 bridges closed, 12 roads closed. It's really hard to move materials and equipment when your entire system is shut down. 2007 was probably the most devastating event I've ever seen. Hopefully it's the worst one I ever do see. Very small watershed, 9.6 square miles, extremely destructive. We lost 4 lives, one of the bodies was never recovered. Homes were lost. Some of the people watched their homes be washed away. Officially, we had 6 to 8 inches in a 2-hour period. Unofficially, we had 11 inches in 4 hours. $12 million in damage to a section of highway that's about 7 miles long. This is the hydrograph for that event. Anyone that tried to turn this hydrograph in college would be failed immediately. The leading edge of that hydrograph, as Stuart showed, should be a nice uniform increase in the flow up to the peak. And then the recession leg is typically quite a lot longer as things dry out. This is the Beaverkill River just immediately downstream of where the flooding event hit. It went up 7 feet in a 15-minute period. This was a wall of water that came out of this watershed. We had firemen that said as they attempted to come out of the valley, this wall of water was actually picking up the back of the fire trucks and shoving them to the side. My wife and I sat about 12 miles away on our porch having a beer when the phone rang and said, well, we just lost 107. So what are you talking about? Lost 107. It's not even raining here. 2011, as we get better, we lost less bridges, only 5 structures lost in Irene, 20 damaged, $15 million, certainly not nearly as bad as Green or Ulster or even Sullivan or Cary County. But that's the National Weather Service showing the intensity. You can certainly see the real high intensity rains falling in the Catskill Mountains. There's a lot of rain that comes down quickly and it runs off quickly. So what have we learned? The number one lesson is we have to work with nature. We're not going to win. We cannot design our way out of this thing. We have to get smarter. We have to understand where we can develop and where we can't develop and keep that in mind at all times. Unfortunately, water is a big part of our history. A lot of transportation in the early development of this country was along water courses. We developed all of our infrastructure along these water courses. And now as the climate changes and it's going to destroy us, we have to move from that old infrastructure to new infrastructure in locations that is a lot more resilient to flood. We have to keep the big picture in mind. Because a lot of time engineers run out, we focus on what's damaged, we just repair what's damaged, and we don't see the big picture. And that was one of the biggest lessons that I learned in '96. We did a lot of work, we upset a lot of people. Trout Unlimited challenged the DEC as to permits given to us for recovering. There was actually a battle in the San Francisco Times between the chairman of Delaware County and Trout Unlimited on a national level. What it did was bring a lot of people's attention to Delaware County, and we're in the city of New York's watershed. So New York City DEP brought in Dave Rosgan, who's a nationally renowned geomorphologist, to kind of point out to us what we were doing wrong. And I learned an awful lot from him. In subsequent years, we've had our engineers trained by him. And one of his biggest points to me is that you run out and you fix all these damaged spots. You never stop to think about those sections of stream that are 5 miles upstream that came through this event without any damage whatsoever. Why didn't you look at that? Why didn't you try to learn from why did it work there and not here? So probably the most important lesson I've taken away from a very enjoyable career is that I really need to observe what we do, look at the big picture, and not get too carried away with individual projects. Flooding resilience is not cheap. We, as municipalities, have taken a lot of abuse for trying to over-design things so that they stand events. We take very seriously your tax money and try to make sure that we design things that can last. And the environmental groups are very critical of what we do, but it's been really reassuring in the last 3 or 4 years as environmental groups get more and more money and they come say, we'd like to fix the stream. We've got this money. I said, that's great. You're only about halfway to what you need to do it right. And they look back and say, oh man, can't you do something with this money? I said, yes, but you don't want me to, because it's not going to solve the problem. Some of the important things that we've learned that we have to focus on is stream alignments, hydraulic capacity, scour, and structure types. Alignments. A couple of case studies. This is one that really Trout Unlimited held up in my face to show me where I was going wrong. This is about 11.3 square mile watershed. Some of these photos were obviously before I joined the county, but we'll start at 78. We'll see the stream starting to migrate around. 96, we get hit with the tremendous flood. Yours truly goes in, designs a nice trapezoidal channel. Looks good, doesn't it? Except it started to deteriorate very quickly. Fall of 2003 looks like this. Summer of 04. April's event in 05. June of 06 is another flood. You can see it moving all over in that floodplain. So Hancock comes to me after June of 06 and says, you got to straighten that out. I said, the first time I did that was my mistake, or the good Lord's mistake. I can't do it again because it's going to be mine. So, because the county didn't do it, the town went in and did it. They did it in 2006. November 2006, you see what it's doing already. It's moving. We cannot design our way out of these things. This particular project is really an issue because of its proximity to the main stem of the East Branch of the Delaware. It's in an alluvial fan. Alluvial fans move. It's a natural thing. No matter what you do on this alluvial fan, you're going to fail. You need to get away from it. And we as humans need to evolve and learn when we can fix something and when we can't. So September of 08, fixed again. Irene comes through. There's no solving this until we move that road and move the bridge. Horsebrook in the town of Colchester. Damage in 96, we cleaned it out. It was a poster child for TU and Delaware County DPW actually working together. We reconstructed it in 98. TU designed the stream. DPW engineers designed the waterway opening. We put in some floodplain drainage in order to keep some of the water on the floodplain instead of trying to focus everything into the bridge as we get to the crossing. It's a relatively small watershed again, but it was a great opportunity. This is what it looked like in 96 when I cleaned it out. Again, you like my trapezoidal channels? I'm pretty good at it, except they don't work. By the next year, you're starting to see a depositional feature occurring right in the center of that channel. We've over-widened it. It doesn't have enough capacity during the low bank forming events, the 1 to 3 year events. It's too wide, there's no energy there, it can't carry that through. So it forms a center bar, builds up and makes a mess. This is Trout Unlimited's design. Step pool, really nice looking. We put floodplains on the sides, graded them all out. Trout Unlimited planted some vegetation. Looks good, doesn't it? That didn't work either. The problem again is you're on an alluvial fan. You're at the confluence of a small tributary stream with the Beaverkill River. When the Beaverkill is in flood, this little trib comes down, the water stops, drops its load no matter what we do. On the right side of that picture, as you're looking at it, right across the road, it is the Beaverkill. So again, we need to get smarter about where we apply your money to make sure that we're sustainable. Yes?
Can you define alluvial land for us?
Can I when I'm finished? Because I'm going to run out of time anyway, but I will answer that question for you. That's standing on the road looking upstream. You can see how big those depositional features occur. That's on top of TU's design. So those step pools are still under there. We went in, we carefully excavated that gravel. That's looking downstream up underneath our bridge. So you see the magnitude of that depositional feature. We cleaned it out carefully. Mother Nature fine-tuned it. You can see our step pools are coming right back. This is another kind of case study. The bridge closed sign that you're looking at is that bridge that was damaged in '96. We fixed it in '96 by putting in some scour protection. In 2004, it got damaged again. 2005, April, did it in. So we designed a new bridge for that location, and we had it all fabricated. We sent it out to be galvanized, and we had it just about ready to go in when 2006 hit. So you can see the bridge from the same perspective that the previous photo was just taken on. Is way up here, and the stream's down there. What do we do now? This is what it looks like from an aerial. Big picture again. You need to get beyond just replacing what was there historically. The photo on the right shows where the bridge is. Stream's coming down. It's got a terrace on the side, terrace over here, which Stuart talked about. Kind of bank fits into this gravel terrace. Makes quite a sharp curve, goes underneath the road and comes down. After the event, it's a lot smoother. The old bridge was up here. So you go upstream, look upstream a mile, look upstream 2 miles, get your pattern, do the geomorphology on it, figure out where that stream really wants to be. At one point in history, as Stuart said, it bounced back and forth between the terraces on both sides. That whole bandwidth is free reign for that river. Whatever we're doing inside of that, we know that we are not going to outlast Mother Nature. But we have to do the best that we can with what we have. So, we probably did over-design it a little bit, but engineers don't like to fail any more than anybody else does. So, we left the channel where it belongs. We did put in some Roskin veins to try and turn the velocity away from the bank and get it out into the stream. And that's our finished structure. Town of Colchester, 2007. I'll try to go through these relatively quickly, but 9.6 square mile watershed. These aerial photos were taken by a local pilot that went up in the air that morning, and these photos have taught us an awful lot about what we do wrong. Obviously, you can see County Route 7 here. This is Beaver Kill Road. This is where the stream is supposed to be. When I say supposed to be, this is where humans would like the stream to be. The actual center of that valley is right where the water went, obviously. Undermine this bridge tremendously. So as we fly our way up the valley now, you're going to see where historically the stream was relocated in order to accommodate a nice straight road so we can all go 55 or 60 miles an hour. Heaven forbid we slow down to 45. We as engineers are challenged to design new roads and build new roads that you can go 55 or 60 miles an hour in a snowstorm and not worry about getting hurt. So we relocate the channel and design you a good road. So it was over here. Guess where it went? Back where it wanted to go, undercut the road by 7 feet. We go a little further. A couple of things here. Number one, yours truly makes the road even straighter about 7 years ago because the old road came over here. We had a number of accidents on that curve. So I pulled the curve in, straightened the road out. However, I undercut this little tributary coming down here, less than a square mile in that little watershed. I undercut that alluvial fan, never anticipating an event like this. But I will never, ever do that again. Because the one thing I will take exception to Stuart on, when he showed you those big rocks and said they won't move, they will move. There's over 8 feet of material that came down out of that watershed that got dumped on top of the county road. There were rocks up there bigger than these tables put together, leaning up against trees. Just an unbelievable event. And when the climatologists say that we're getting worse events, it's time for me to retire. I've been through enough of these. That's how much material we had on the bridge itself. That's the little trib coming down to your right. The main stem of Spring Brook is underneath that bridge. Go
2006?
2007. 2007, very isolated event. Only 9.6 square miles. A real anomaly. 11 inches of rain in 2 hours. Okay, this was not a widespread thing. Very isolated event. But we see more and more of them, so we have to design for this. So I'm further upstream now. The stream has been pushed over against the base of the mountain so that the county road can be nice and straight. Where does the stream go? Right back to the shape that it wanted. Natural shape of that channel, sinuous, designed to dissipate energy, to use its floodplain to dissipate energy as it's coming out of there. We take that away from it, it takes it back. There's a number of sections of that road that we had to walk with GPS units to try to find bits and pieces of that double yellow line, because that's the only thing we had to try the county road back where it was. There were stretches over a half a mile long that were completely wiped out. That's the center line of the county road. That's actually a tangent. Further upstream, again, we put in a bridge, we push the stream over against the bank, nice straight alignment for the road. It will take it back. And probably the most impressive, you're only about, less than a half a square mile in watershed at this particular point. When you go back and look at the 1943 plans where this county road was built, that's exactly where the stream was. They pushed it out of the way, made the road down through there. Now it's over 14 feet where that stream took that in. Now we're not talking about hundreds of thousands of acres upstream. We're talking about less than a square mile watershed at this point. Again, as we design our roads, this profile is actually coming down. This is a little tributary that comes in, no culvert across there. What's our design standard for small culverts? We'll probably design that for a 25-year event. And we'll design the pipe so that it's got an HW over a D, or a headwater over the depth of the pipe of about 1.5. Because pipes are a whole lot more efficient when you put them underhead. So if you had 2 or 3 feet of head over that pipe, it passes a lot more water. So you can put in a smaller pipe. Wrong. When that thing overtopped, what happened is that because the road's not in a sag vertical curve, so if it's in the bottom and the water comes up and runs over the road, big deal. You lose a couple hundred feet of road, not a big deal. But when the county road is on about a 3% profile and it comes up, the controlling headwaters is the ditch. So the water doesn't run across the road, it turns and runs with it for like a quarter mile before it finds its way back into a water course, wiping out all your shoulder, undermining the pavement for that entire length. Short sheeting design requirements for small crossings is not a good idea. That's the inlet end. When it gets so overwhelmed with hydraulic capacity and starts to slow down and drop its load, it drops all that bed load, it plugs the thing right up. That's what it's supposed to look like after we clean all that out. That's about 8 feet of gravel that got deposited at the inlet end of that pipe. Now you're less than 2/10 of a square mile. Again, undersized pipe, saved a couple of dollars at some point in history, thousands of dollars to try to recover this thing. Scour. A lot of things we learned about scour. This particular bridge is what they call an integral abutment, which is a new New York State DOT design standard, which we all thought we could save some money. It was a good application. So you can, that photo doesn't show up nearly as well there as it does on the screen, but there's nothing under it. You can see it better there. There's nothing under here. This is the old part of the abutment. I left the old abutment in place. That'll make good scour protection for our new bridge. So we won't have any scour along that abutment. Wrong again. When you build something hard in that stream, create that hard spot. The water goes over that, and it actually digs on the backside. The shear stresses in the water around that hard spot just create tremendous turbulence and eddies that when they scour underneath your bridge, they make a mess. So no longer will I leave any concrete in a stream. The more that you can get that replicated to what's natural, the better off you are as far as having chances of being sustainable. Kind of hard to backfill underneath an abutment when the abutment's over your head. It's just, that was poor design, and I'll never build another one. That's looking underneath the footing. This is actually the footing of a bridge. These are the piles. That particular bridge I wasn't really worried about because the record plans showed that it was on piles, so I didn't think it was going to settle. Within about 3 days, we started to see some settlement. Back to the record plans, they were 13 feet deep, those piles. Obviously, the scour was in excess of 13 feet. And we found evidence afterwards, some of the debris we had taken out, where that, at the height of that event, it had scoured out over 13 feet below that bridge. During the recession leg, as things slow down, it drops that material back in there. So when you go back and look, you don't think anything really major changed. However, during the height of that event, there was not only water, there's woody debris, there's gravel debris, everything else is traveling in that channel, and you have to design features that will accommodate all of that. So what have we done? We've adopted hydraulic and hydrology standards on the county level that exceed DOT's, and we have to be able to spend county dollars effectively. We need to get some of our duplicative infrastructure out of the air. We need to find out where the real major crossings are. Some of the minor convenience structures need to be removed. We can't afford them all. We can't afford to rebuild them. We've gone to 3-sided boxes. Trout Unlimited says that's great. We have a natural bottom in the bottom of our crossings now. I'm here to tell you that, yes, it is good for habitat, but it's even better for durability for structures. If you design structures that are really durable, the habitat is going to be there. It's a win-win. We have to be able to work together. Floodplain drainage is very, very critical. We need those floodplains to be part of our river system. We cannot build berms. We can't try to channel. You've all seen what happened to the Mississippi and the Midwest, and we need to learn from that and learn from that quickly. So we have adopted those standards. We've gone to the 3-sided boxes. This is a problem pipe for us. That was about a 6-foot diameter pipe. When you're standing on a pipe looking upstream, you can see the bankful width of the stream as it comes up through the You'd think that would have told us something. Just looking at it. Look at the size of this pipe and look at the bankful width. Doesn't that tell you something? So, again, along a profile, Controlling headwaters, the ditch, not the road. So when it gets overtopped, runs down, wipes out a very long section of road. We replaced it with a 3-sided box. You can see when we put it in, when we drive the sheets, and we use sheet piling as opposed to concrete because it does less damage to the natural soils around it. We disturb less soils, so there's less soils that are actually mobilized during high flow events. But when we put this in, you can see where the soils were. The one thing we didn't accommodate for here was the amount of head cut that was going to occur after we did open it up. So again, you got to keep the big picture in mind. You got to look downstream, upstream, not just that you're crossing, you need the whole picture. Is there a head cut coming at you? You need to design for that. Take that into account when you're sizing these structures. Floodplain drainage. From an engineer, this is the goofiest thing I ever saw, but it works. This is County Route 2. This is our main structure. It's about 120 feet in length. This is on the west branch of the Delaware. And one of the things that Roskin tried to get me to pay attention to is keeping water on the floodplain on the floodplain. Don't try to force it all into our opening at the bridge itself. So there are 6 floodplain pipes, 6-foot diameter pipes in the approach, so that we can keep water that's on the floodplain traveling on the floodplain and keeping debris that's on the floodplain, not plugging up our bridges. We've had farmers' round bales plugged in the end of these things, which is a pain in the neck, but I'd much rather have it here than in that bridge. That's downstream of the same structure. This is a structure that was destroyed in Irene. This is a very good bridge. One of the best bridges we had as far as condition rating, but it was not founded on piles. It was just, the bottom of the footing was about 5 feet below the fairway, and during the height of the event, because of when this structure was designed and built in the early 40s, they built all this approach fill, cut off the floodplain, focused all the water underneath there, and then scoured, during Irene, scoured right underneath this abutment. The wind fell off first, the stem wall tipped and fell in, settled over 4 feet on this end of the bridge.
About 5 minutes.
Thank you. Our design, this span is the exact same span as the original bridge. Takes our low flow, but we put in floodplain drainage here. We excavated upstream and put a floodplain in. You can see the high water mark in this event. It was post-Irene. During high flow events, the water stays on the floodplain, goes underneath that second span. Cost of that bridge about 1.5 times what a single span would be. But now we're assured that in future events we're going to pass it. A couple of things we've done for pipes for towns is to help them try to increase their infrastructure from small pipes to adequately sized waterway openings. In 2011, we replaced a 9x5 elliptical pipe. As you can see upstream, they have built berms along the stream to try to focus the water into that crossing and keep it from flooding their roads. Looking downstream, you can see the height of those berms. And what are they trying to focus water into? What is that? When you look at the width of that compared to the bankful width of that stream, I mean, that just tells you immediately that that's undersized. You can go through the numbers and put enough head on that to actually pass the water alone, but not the debris, not the woody vegetation and everything else. And corrugated metal pipes that rust out at the bottom actually rolls right up in the height of an event with all the water going through there, plugs them, and then the water's going over the road, and the water's washing your road out, and you're in real big trouble. This is after we've regraded the entire water or floodplain, and that's the structure we replaced it with. Size for a 100-year event. Is it cheap? No. It's probably twice as expensive. But in my mind, if you look at the life cycle cost of doing it twice or even 3 times in the life of this being here, short of a tremendous act of God, will be there long after I'm gone. And I've got one more to show you. This is one we did for the town of Stamford. We did this with New York City DEP money. We're in the city's watershed, as I indicated. You can see about a 6-foot diameter pipe there. Washes out every year. When we went through the hydrology and hydraulics, recurrence frequency for overtopping that structure, 1.5. So every year and a half, they would expect that to be surcharged. And it did. So you can see the original structure inside of our new abutments. Give you an idea of the magnitude of how we had to open that up. That's our completed structure. And we're confident that that's going to withstand a whole lot more events. But the question was asked about as recurrence frequencies change. The 100-year event that I was graduated from college with is now the 80-year event. Those recurrence frequencies are nothing more than probability. It's taking the history and all the events that we put together and projecting that forward. So as the intensity and the frequency of events increases, then what we have to design for also increases. So, and we need more of a factor of safety than what we've used in the past. I'd like to recognize some great partners as we've learned through this. I wasn't the only idiot. Delaware County Soil and Water has worked very closely with us, and they are actually the ones that put the post-flood stream intervention package together. They did an awful lot of work on that and really are leading the way for flood recovery. Delaware County Planning Department, County Watershed Affairs, and New York City Department of Environmental Protection. Sometimes we all complain that the city's over-regulating us, but they have really come to the table and helped us try to design and build more durable infrastructure. You design for good habitat, you're going to have durable infrastructure. You design for good infrastructure, you're going to have good habitat. There really is a marriage. I didn't think there was in my younger age. I thought it was us versus them. But we really are in the same boat together. We just have to get smarter. Thank you.
How about a couple of questions, and then we'll take our break.
I think the first question was, what's an alluvial fan?
Okay.
An alluvial fan, as you look at any stream, as it comes out of the mountains, as its gradient changes and comes into the valley itself, that's where it starts to lose its hydraulic energy, and that's where it starts to drop its bed load. So as you look at an aerial photo or a topography map of any area where there's major stems and tributaries, you will see a fan like a delta out into the main stem valley, and that's all debris that's come out of the tributary and been deposited there. So it's, does that explain a little? And they're very active areas because as more and more material is eroded out of the mountains, not necessarily human, it's a natural erosion effect until the good Lord makes this earth flat. It will continue to occur, and as it slows down, it just builds a wider and wider delta. Yeah.
Maybe this will be covered later, but if one wanted to take these lessons that you've learned back to one's own municipal DPW, as they deal with their culverts and washouts and small bridges, what resources can you point us to that would help us do that?
As far as money or technical resources?
Technical resources. Money's good too, but, you know.
Money is good, but money's hard to get. And in this economy, it's even harder. As far as technical resources, there's a number of good documents Dave Roskin has published on geomorphology, and there's a lot of good stuff on the internet. Some of my hard lessons aren't documented very good, but maybe someday I'll put them in a document somewhere.
There is going to be more of these post-flood stream intervention trainings taking place. 2 occurred in the Cary watershed this past spring. But our local soil and water conservation districts are being trained, if they aren't already trained, to deliver some more of this education. Especially they're working with some of the materials that the Delaware County Soil and Water Conservation Districts have put together. But they're also in conversations about how to adapt that to different areas, because our streams here in this area react differently. We don't have the same types of elevations that are going on, say, in the Delaware County streams, and even are reacting differently to streams in the Catskills. So they're in conversations on how to make that information more applicable to individual areas. So my recommendation would be to either contact your local soil and water conservation district, or take a look at the Hudson, the Estuary Resiliency website. It's on some materials. So our project is to try to bring all these resources into a location so we can easily find them and take them into that maybe.
Delaware County Soil and Water does have a webpage, and their design document is there. But a lot of their known graphs and stream sizing charts are based on the geophysical area of Delaware County and specifically Catskills. So those charts aren't directly applicable, but they at least give you a process that you need to follow.
Okay, let's take a 15-minute break here. We'll reconvene sharp at